So, first question. How many forces do we have? Two forces. Okay. What very important feature are we told about them in the heading of the question? They both have the same what? Perfect. So they have the same size, strength, amount, whatever. Okay. What could be the angle between the two vectors, obviously tail to tail, if their sum or their resultant or their vector addition has a magnitude of? Okay. So, sorry, not that. Yes. A. How could you add two forces? Listen up, everyone, come on. How could you add two forces such that the magnitude is perfectly 2F? By the way, all you have to do now is basically think, how could you orient two vectors? Because again, are those two vectors identical as far as magnitude is concerned? Yes, not angle, but magnitude. Obviously, you can hold them in how many ways? An infinite number of ways. So the question is, how would you tell me how to actually hold these two vectors such that their addition is exactly double each one of them? Here's the question. Is this correct? If you hold two vectors like this, whoops, if you hold two vectors like this, what are these two vectors oriented with respect to each other? They're what? They're opposite to each other. So if you, by the way, those vectors represent what? Represent what? Forces. So if Ammar is pulling this way and I'm pulling this way on an object right here, what would happen to this object eventually? Would it move? Exactly. So that means what's the magnitude of the force on this object if two people pull like this? There we go. We just solved for what? We just solved for C. Okay. So my question now is, how would I orient these two vectors to actually make the resultant vector 2 times F? How? Pointing in the what? In the same direction. Why? Because I can move this one to go where? Right here. Those two vectors, are they against or perfectly with each other? Which means what? If Ammar pulls this much, and I'm basically pulling also on the same on the same object in the same direction, it's like how many people are pulling? Sorry, it's two people pulling, but each one is doing what to the other? Canceling their force or adding to it? Adding to it. Who would like to do part B? Josh? Hold. Okay, go ahead. Put these vectors tail to tail in a way such that when you add the resultant, you would actually have square root of 2 times the F. It had to be what? Perfectly what? Perfectly perpendicular. Why? Because when you have this on the X and this on the Y, how would you calculate this guy? How would you calculate this guy? What do you do? No, if I just want the length of the diagonal when two vectors are perpendicular, what theorem do you just apply? Pythagorean theorem. C squared, sorry, C squared equals what? A squared plus B squared, which means F squared plus F squared, and then you take the square root. What's the square root of 2? Square root of 2. And the F comes out of the what? Of the what do you call it? Of the square root. Okay? So let's actually what? Write each one of them explicitly. Where's the thing? Okay. So part A. So we're going to say the forces must be opposite or parallel for the magnitude to be double. Exactly, because basically both people have to be pulling together without any angle difference between them. Parallel. Which means, there we go. F, F. Okay, let's do C first, because A and C are perfect opposites to each other. C. For C, the forces must be opposite. Which means, so one of them has to point this way, and one of them has to point this way. Again, you can put everyone. You can put a dot here to signify that someone is being pulled perfectly in the same direction. Sorry, in two different directions. B. the forces must be what? What to each other? Yeah. By the way, everyone, never say the forces must be, because we said there's another word for perpendicular. What is it? What's another word for perpendicular? Come on, we've been using it a lot with forces. Come on, starts with N. It's the name of a force. Normal. Never say forces are normal. Say they are what? Say they are perpendicular. Normal is when you relate a force to a surface. I know it has the same mathematical meaning, but when it comes to terminology, never say two vectors are normal. Say two vectors are perpendicular. The forces must be perpendicular. Perpendicular. Perpendicular, which means one F has to be this way. Uh, okay. And one F must be this way. Sorry, they should be coming from the same exact point. I just don't have enough space. And one F should be this way. Make sure you make them like they are a square, not a rectangle. And then you add a hypotenuse. Go ahead. So you say F net equals, and then let's do a calculation. F squared plus F squared. What's F squared plus F squared? Come on, math people. F squared plus F squared. X squared plus 2x squared. So 2F squared. Not what? Not F to the power of what? Yeah, when you add powers, sorry, when you add things, do you get a higher power or just a higher amount of them? Amount. You just get more things. You do not. When do you only get a higher power? When you do what to variables? When you multiply them because exponents add up. Yes. So this is what? 2F squared, which is square root of 2 with F. Done. That's it. Okay. All right. Okay. This actually might be a question that Shivers gives you in Becker. Has nothing to do with physics. At the same time, has everything to do with physics. Okay. Yes, Samar. Uh-huh. Sorry, you said what? Say again. Okay, so everyone, who remembers this from grade 11 radicals? A times B is equal to what? Square root of A times what? Square root of B, which means if this is 2F squared, that could be also what? Square root of 2 times square root of what? F squared. And that's what? F. Does that make sense now? Please stop me at these little steps because you might have forgotten some of them from grade 10, 11. No problem. I am here to review. Okay, Ammar, make sense? That's it. Because of that radical splitting step. Okay, all right. Next question. Okay. So someone needs some jaw support. Okay. So basically, what they do is what they attach like a sling to their jaw, such that it basically what lifts it straight up. Okay, lift it straight up. Okay. Now, so they wear a strap that produces a net what? Net what? Upward, straight upward. So the overall force on the what? Obviously, you want it to be upward because if it pulls slightly to this way, it might actually put more what? Like that. That means this part of the neck could be strained more than this part of the neck, and vice versa. So you just want to make sure that it perfectly just points up, so the whole thing gets symmetrically lifted up. Okay. Net force of how much? Just how many newtons? 5 newtons. Okay. The tension in this is the same throughout the what? Through the strap. However, okay, to what tension must the strap be adjusted to provide what? To provide that necessary upward force. Okay, question. Does that angle look symmetric? What do you think? Obviously, from a from an anatomical point of view, should it be symmetric? Of course it should be. You should not pull on one side of the face, or sorry, one side of the jaw more than one side, which means which means, by the way, which part of the face is the chin directly touching? The what? The chin, right? The chin. So what's our FBD? We're gonna do the FBD of the what? Of the chin. Okay, all right. So let's say that the chin is right here. Okay. Oops, sorry. Yes, go ahead. Okay, everyone. Sorry, I don't know what just happened. Everyone, this 75 degrees. Everyone, this 75 degrees is the angle from here all the way to where? All the way to there. So it is. So you have to actually what? Split it in two. But is it on the horizontal or the vertical if you split it in two? Come on, think. If you imagine a line cutting the face right in the middle, that's 75 degrees. Would have more to do with the horizontal or the vertical? Vertical, exactly, yes. So everyone, go ahead. We're going to sketch what? We're going to sketch the following three vectors. I'm going to sketch a vector this way. Everyone, this is the tension in which part of the strap? The left or the right part? The right part. Is there another tension in the left part? Of course there is. Identical and perfectly symmetrically angled. So go ahead and sketch another one. Oh, well, it needs to be like, come on. Okay, let me do my best here. I think I have stuff. Okay, that's good enough. Let me erase this. Okay. And what should be exactly in the middle? Yes. Which force is 5? This one or this one or this one? Exactly, because they said a net upward force of how much? Of 5 newtons. Perfect. Everyone? So this is 5 newtons. Go ahead. 5 newtons. Now, can someone say again? Okay. We know for a fact that the chin, is it moving or is it standing still? Stationary, which means what? 5 newtons is also equal to what? Is equal to 5 newtons going down. But the question actually doesn't care for the what? For the gravity. It just wants what vectors here will add up to what? 5 newtons. Okay, can someone tell me how would I know how much angle is on each side? What do I just do? You divide it by 2. What's 75 divided by 2? What's half of 75? Go ahead. 30, oops, sorry. 37 and a half here and 37 and a half here. Okay, everyone, let's go to the next slide for the calculation. Bless you. No, go ahead. By the way, in Shiver's course in Calculus of Vectors, he will show you that this could be done in how many ways? 2 ways. Because, by the way, you might see that you have 3 vectors here, but you really have how many vectors? 2 that you need to add to 5. So when you have 2 vectors, how many ways can you use to add them? How many ways did we learn? 2. The vector decomposition, and what was the other method? The cosine sine, the cosine law, sine law. I want you to use the what? The vector decomposition. Yes, they do. No, but that's the again. Okay, remember the only time that two forces perfectly add in a doubled way is if they're pointing what? Straight up. Sorry, straight in the same direction. Whenever there's an angle, trig work has to be done. Okay. All right, everyone. Let's go to the next slide. So, okay, what we're gonna do is this. Okay, one. They should be symmetric. We're gonna call this one what? We're gonna call it what? Now, do we need to call them T1 and T2? Are the two tensions the same or different? The same. So if they are the same, just use the same the symbol. So T and T. Okay. And this one was theta, and this one was also what? Are those vectors bad or good? Those two vectors. Come on. Bad, which means both of them need to be what? Need to be decomposed. Okay. Go ahead. Okay. Do you see, everyone? Does it make sense for both of these to perfectly line up twice here? Of course it does, because they are identical. So just make another arrowhead as well, just to know that there are two vectors on the y-axis. Like this. One, look. I mean, they perfectly should line up, but just for our visualization purposes, just make sure you see two, because we're gonna need to add these two. Okay, now we can start. F net on the y equals, oh, this is the y, by the way, and this is the x. Can someone tell me if this is cosine or sine? Why is it cosine? Because this and this angle are what to each other? Adjacent. Done. So F net on the y is t cosine of theta plus another what? Can someone tell me why there are two? Oh, yeah, I'm going to add them up right now. Everyone, obviously, what's t cosine theta plus another t cosine theta? 2 t cosine of theta. But I'm just, starting the process here. So that means F net y equals 2 t cosine of theta. But what did the question say that the net force on the chin is? How much? 5. There we go. 5 equals 2 t cosine of, let me just put it sideways a little bit. And what was the angle? Yeah, not 75. 75 is the whole thing. I just need one side. So 5 equals 2 t cosine of 37.5. How am I going to solve this? Physics is done. Math takes over. How do you solve this? Exactly. You need to isolate the t, which means you need to divide both sides by 2 cosine of 37.5. So t equals a big fraction, well, a fraction, 5, 5 divided by 2 cosine of 37. Who's got this? Please, if you're going to do this with a single display or even with a double display, make sure you put these two in a what? Yes, in a bracket. Otherwise, if you do it just as a single line, you might end up multiplying by cosine 37.5 instead of dividing. Okay, Josh, you're getting 3 points. How many people are getting 3.15? Great. So 3.15 Newton. Ammar, is that half of 5? No, exactly. Oh, remember everyone, just because they are both identical does not mean you just take it and divide by what? By 2. You only divide perfectly by 2 if there is no angle between the vectors. So let's write a therefore statement. Therefore, everyone, therefore, or you can do the therefore the 3 dots like we do in math. Therefore, each side should have tension, should have tension set to, like you should tighten the what? You should tighten the strap to actually what? To be at a tension of 3.15 Newton. If you set it to that tension, everyone, and they are 75 degrees open, you know that then your chin is going to be lifted all the time at 5 newtons all the time. If you change the angle, would it change this number? Of course. I mean, you don't even have to guess. Look at the equation. If 5 stays the same and 2 stays the same and you change this one, would this number change? Of course it does. Done. That's it. Okay, come on. A 68.5 skater moving what? Moving initially at what speed? Speed. Is there any equation in forces that has speed? No, the only equation with kinematics and forces is what? F net equals? What's Newton's second law? F net equals ma. So again, remember, the only thing important in forces is acceleration, which means if you're ever given speed or distance or time, you know we're gonna have to go back to what? To kinematics at some point, before or after, at some point. Okay, initially moving at what speed? Come on, 2.4 meters per second. On what? Rough, horizontal, ice. Comes to what? Comes to rest. Again, another kinematic information telling you what? What does it mean when something comes to rest? What's perfect deceleration, which means eventually, what's the final speed? See, now we know two numbers. We know VI, we know V0. Uniformly, which means what? In a uniform acceleration kind of way. In how much time? Do we have three kinematic information? Yes, we do. We have to start with kinematics. Okay, all right. Let's start with kinematics. So I want you to actually say start with kinematics. So start with kinematics. Okay. What are my kinematics information? Vi equals how much? 2.4. Don't worry about units. All of them are standard and good. Vf is what? It came to rest, so it's 0. And delta time it took is what? 3 point, how much? 52 seconds. Okay. According to kinematics, I could want to find what or what? According to kinematics. Remember, kinematics has what? Has 5 kinematic variables. Out of them so far, we know 3. I could ask you technically for 2 things, either what or what. I could ask you for distance or displacement, or which one is important for forces? Yeah, because F net equals ma, not m delta d. So always shoot for acceleration. So I need acceleration to equal question marks here. All right, acceleration equals question mark. What equation do I need? 1, 2, 3, 4, or 5? Which one? Why first one? Because apparently which variable is missing from the list? Missing, not unknown, missing. This distance or displacement, which means equation number 1. So let's do equation number 1. What's equation number 1? You, exactly. It's the definition of acceleration. All right. So I'm going to do it a different color. So A equals Vf minus Vi over delta t. Great. Is this a solving or a plugging in step? Yeah, because everything I need is here, here, and here. So you just plug in. So A equals 0 minus, how much? 2.4 divided by 3.52. All right. By the way, is this going to come out to be a positive or a negative number? Of course negative, because you're slowing down. Great. Okay, negative. How much? I have my calculator here, so we can do this together. Uh-huh. I'm gonna skip the fineness because I know it's there. 3.52. Okay. By the way, what's the specific situation in the entire problem? 3. All of them are 3. So let's take it to intermediate step to be what? 4. Yeah, always go one more, just to make sure that your final answer does not suffer with precision. So if this is 4, how many? 6, 8, 1, 8. Sorry, say again? No, 2.40. Remember, extra zeros are okay. Remember, stepping on a scale and seeing an extra 0, that's very sensitive. All right, negative 0.6181. In what unit? It's acceleration, meters per second squared. Okay. All right. So far, so good. What's the question asking? Yes, Josh? Listen. Okay, have a question, everyone. Eyes on me. Skiing, right? Initially, what was the speed? 2.4. And then they came to a what? Stop. Was someone pushing them, or they were just slowing down on their own? They were slowing down, well, on their own because of friction, right? So that means, okay, everyone, imagine me skiing and just coming to a stop. During my deceleration, what forces are acting on me? First, what's the first force always? Gravity is pulling me down, but I am on a surface. So what? Okay, am I moving down or moving up? So that means Fg and Fn on me are what? Equal. Is someone pushing me? You could say, aren't you pushing yourself? You can never push yourself, right? You push the ground and the ground pushes on you. But I am slowing down, which means the only force acting on me is what? Friction. With me or against me? Perfect. So my FBD would have 4 forces or only 3? 3. Fg, Fn, and exactly. So, and F, okay, Fs or Fk? Fk, because I don't care if you're slowing down, you're still in what? You're still in motion. All right, so go ahead. Just sketch. Remember what we do. We don't sketch anything but a box. Go ahead. Fg, Fn. Okay, I have to decide now on a direction of what? Direction of motion, because once I know how they're moving, I will know how friction is acting. So everyone, let's say they're moving this way. Motion, which means Fk has to be that way. Great. Is this, everyone, is this question asking me what's the mu k? Could they ask it? They didn't. So I don't really need the what? The mu k equation. I just need the Fk equation. Sorry, the F net, I mean. So go ahead. F net equals ma. By the way, do we really care about the y-axis? Why not? Why don't we care about the y-axis in this particular problem? Because I'm not sinking in or jumping up. I just care about the x. So go ahead and write x right here. Do we know the mass of the skier? Or the scalar, sorry. How much? 68.5 kilos. Okay, I'm going to take a vote here. How many people say we should use the negative of the acceleration in this equation? How many people say we have to? Okay. The question is, we got a negative acceleration, which makes perfect sense because you're slowing down. How many people say I have to multiply now by negative 0.6181? How many people say we should? How many people say we don't have to? Okay, I need someone to Jinan, why would you say we don't have to? By the way, the reason I'm taking a vote is that both answers are correct. But it just depends on how you interpret your answer. Jinan, why are you siding with no need? Just use this number without the minus. I'll give you a hint. Is the question asking what magnitude or just what force? If it said what magnitude, can you ever get a negative answer? So then you're forced to just use what? The positive magnitude of the deceleration, right? But they're asking what force. Could force be negative? Hassan, what do you think? Sorry, you said yes or no? Could force be negative? No. How many people say yes, it could be? Okay. Aren't both answers correct? Depends. If you think of force as a vector, could it be negative? Of course it could. Any vector could be negative. But if you really think of it as a physical amount, then it has to be what? Do you see how much freedom I'm giving you to interpret the answer? If I ask you what force, by the way, technically, a university professor would want you to put the negative, right? Because force still has a direction. So it still needs a what? It still needs a sign. But did you already give me a diagram? Do you really think I need a direction anymore? Nope. I just need what? I just need to know how much force is friction pulling them with. So do you think we should use the minus or no? How many people don't want to use the minus? I don't want. All right. So go ahead and just multiply by 0.618. Whatever that is. 68.5 times 0.6181. What's the specific situation in the original numbers? 3. So that will be 42.3 because this 3 does not do anything. Done. So 42.3 Newton. So that means what? Ice is applying 42.3 newtons of friction force on that skater as long as they're coming to a stop. Okay. Point six. Oh, 6, 8. Oh, I wrote the number incorrectly. My bad. Sorry. It's 818. Thank you. So what's the answer? Yes, go ahead. Sorry, 40? 46.7. How many people got this? How many got 46.7? Yes. Oh, I copied it even. Oh, good, good. All right, thank you, thank you. Everyone, even here it was incorrect. Okay, now everything is good. Thank you. Okay, I'll read it. Just pencils down, phones away, focus. A dock worker applies a constant what? Horizontal, good, no angles. Horizontal force of 80 newtons to a block of ice, a box, on a smooth horizontal floor. The frictional force is what? Even easier. All right. The block starts from rest. Kinematic information, Vi equals 0. Moves how much distance? 11 meters. Delta D equals 11. In how much time? Delta T equals 5. Perfect. I have 3 kinematic things. Okay. Question A. What's the mass of the block of ice? Wow. Jumping from kinematics to mass. I have to do kinematics first. Okay. Let's do so. Part A. Everyone, do we have 1 slide or 2 slides? Perfect. 2. Awesome. We have a space. Okay, everyone. Part A. Vi equals 0. Delta D equals 11. Delta T equals 5. Should I be asking for V final or acceleration? Of course, acceleration. So acceleration equals question mark. Okay. What equation should I use? Okay, what's missing from there? Missing. Final. Which equation has no final speed? 1, 2, 3. Everyone, equation number 3. So delta D equals Vi delta T plus 1/2 A delta T squared. What's the good news about Vi? 0. So it kills this term. Everyone, remember my style. Just cross it out like this and write 0. It means this goes to 0. That's what this notation means. Okay, good. So this means 11. Is it? Yeah, it is 11. Equals 1/2 times A times 5 squared. Okay, what would that be? Well, if you 5 squared is 25 times a half, that would be 12 1/2. So if you do 11 divided by 12 1/2 from here, you get A equals 11 divided by 12 1/2. How much is that? Well, that's almost like 0.8 something, or maybe no, it's not 0.9, it's 0.8. 11 divided by 12 1/2. Yep, 0.88. Perfect. Nice. In what unit? Meters per second squared. Did we solve the problem or not yet? No, they did not ask me for what's the acceleration of the block. They asked for what's the mass of the block. What's the mass of the block? Okay. Do you think I need an FBD? Yeah. Let's sketch a quick FBD, everyone. So a quick FBD would be this. Oh, sorry. A quick FBD would be this. Here it is. Cool. Okay, good. Everyone, here is my block. What's force number 1? Gravity. Force number 2, normal. Force number 3, someone is pushing. Applied. Let's say they're applying this way. Any friction the other way? There should be, but they said what? They said negligible. Good. Should I do Fnet on the Y or Fnet on the X? Yeah, I mean, Fnet on the Y is just 0 because it's not jumping in, so jumping up or sinking in. So Fnet X equals MA. Do I know the mass of the block? No, but do I know the acceleration of the block? Yes, I do. Do I know the F net X on the block? Yes, I do. It's what? It's F applied. Great. 80 equals M times 0.88. Done. Divide 80 by 0.88. What would this be to? Is it 2 or 3 sig figs? 3. What would this be to 3 sig figs? 90.9. Can someone tell me what they understand from part B? If the worker stops pushing after those 5 seconds of pushing, so what do they basically do to the block? So they what? They let go. Is there any friction here? What's going to happen to the block? Is it ever going to stop? Again, it will, we know, but because there's no friction, this is like in deep space. Okay, so the question is saying if they move it for 5 seconds actively with an applied force, and then they let go, it's going to move forever, right? Good. The question is, how far is it going to travel in 5 seconds more after the original 5 seconds? What do you think kinematically now we need to solve for? Say again? Final velocity. Everyone, look. There you. Okay. Josh is the block. Yep. Okay. Everyone. Space there. Wait. Okay. Okay. What's his speed right now? 0. Any friction here? No. I'm going to start pushing. Just start moving very slowly. I'm pushing. What's happening to his speed? He's what? He's accelerating. I kept pushing for 5, and then I let go. Okay, Josh, once I let go, you have some speed, right? Which is called what? Final speed. Can you ever accelerate anymore? Because it's like projectile motion, right? Nothing is pushing on you, but you're also not being what? Not being dragged back. Which means what? You're gonna go on forever at a various speed or at a constant speed. Constant speed. If I know that constant speed and I know the time, can I know the distance he traveled? Yeah, am I going to use the kinematic equation or the easy triangle? Exactly, but I need to know exactly what Saad said. I need the VF. Good. So everyone, let's go. Thank you, my friend. Let's go to the next slide, everyone. So, let's go here, and we're going to say what? We're going to say we need part B. We need the VF of the pushing phase of the pushing phase. By the way, technically, everyone, I started with knowing how many kinematic information? 3. And then I found what? I went up to what? 4, because I knew the acceleration. Do you think I could use my acceleration as a 4th variable now? Why? Did my acceleration came out to be an approximate number, or did it perfectly round up? What was our acceleration value? 0.88. Was that rounded, or did it perfectly come out to 0.88? Which means what? As far as I'm concerned, is it approximate or exact? So you can now think, well, you know what? I have 4 things I can choose from. You can do that, or you can go back to the original what? To the original 3. Let's go back to the original 3. So what were the original 3? Vi equals 0, delta D equals 11, and delta T equals 5. But now I need my VF. What's missing from this list? Come on. Say again. Acceleration is missing. Which equation has no acceleration? No, has. It's 2AD in the final one. Nope, the 4th one has. The second one, delta D equals have VI VF delta T. No acceleration in the second one. So, okay, 11 equals 1/2 0 plus VF times of 5. All right. Just gonna zoom in. 11 equals. How would I solve this? You just have to clean up. Technically, 0 plus VF is just VF. Everyone? 0 plus VF is VF. And half times 5 is 2.5. So this is just 2.5 VF. Which means VF is what? 11 divided by 2.5. So this is 2.5. 2.5 equals, that would be 4 point something. Yep, 4 point. Oh, whoa, that doesn't make sense. 4.4. 4.4 what? What's the unit here? Yep, speed, meters per second, yes. Now what do? I use a what? I use the what? The triangle, the easy triangle. Here it is, this triangle. Our good friend for cruise control or constant motion. There we go. D, V, T. All right. We want distance, right? So distance, or delta D if you want, equals. Apparently, Josh will be moving at 4.4 meters per second forever. Well, I only care about the next 5 seconds. 4 and 4, 22. 22 meters of distance. Done. That's it. Are those two blocks touching? When two things are in physical contact, what Newton's law do we use? First, second, or third? When two things are, again, every action has a what? Which means when one object hits another, the second object also what? Reacts by hitting back. Are those two objects in contact? Yes, which means what? Between them, there's a what? There's a Newton's what? There's a Newton's what? Third law. Every action has a reaction. Okay, so boxes A and B are in contact on a horizontal what? Horizontal what? Frictionless. Okay. Let me see how many slides do we have. Perfect. We have 2 slides. Okay, everyone. First thing we're gonna do. Okay, everyone, look. Everyone, are those two objects touching? Come on, focus with me. But when I do my FBDs, I like to what? Okay. When you separate them, do they look like touching anymore? But we know they are. I always do my Newton's third law by splitting them, just to give myself what? Space to what? To put the forces in between, like the pair of forces. So everyone, let's do this. So here's my FBD. Okay, everyone, I'm gonna sketch the big one here and the small one here. I know they're not touching, but they are. I'm just cheating with the diagram. Okay, can someone tell me what forces are, actually, let's so call them A and B, right? Yes. No, yeah, A and B. Can someone tell me what forces are on block A? All of them. Come on, all of them. Gravity, thank you. So everyone go ahead and we will do FGA. FGA. What reacts to FGA? Normal on A, right? Because technically it has a different weight, so it pushes the surface at a bigger amount than the smaller one. So F and A. Keep going. What else acts on block A? Is there something pushing it? Of course there is. It says so. Look, everyone. Where are we? A horizontal force of 100 newtons is exerted directly on box A. Good. So I'm going to sketch it going in or coming out. Always. Always coming out of the shape or of the diagram. All right. So this one would be what? Let's say, okay, F applied. F-A-P-P. Any friction. Any friction on either block. They said no. Okay. Everyone, there's one more force on block A. If I push on Shira, Shira's what? Pushing back. So how does that relate to that diagram? Come on. Exactly. box A is pushing on B, which means what? Box B is pushing same direction or opposite direction? Opposite direction. So box B is pushing right here, back on what? On box A. So I'm gonna sketch it here like this. What should I call this force? Come on, remember Newton's third law. How did we denote the pair of forces? I just say what? F of what on what here? B on A. Yes, this here, everyone, this here came from here, which is the F of B on A. Good. FB on A. Okay, now I need someone to help me with the forces on the B block. Come on, come on. Last problem for today. Gravity on B, yes. So FGB. FGB. What reacts to that? F and B. Is there an applied force on block B? Hold on. Is there an applied force directly on block B? No, there isn't. We know it transfers the effect, but we know it's not touching it. Everyone, this is not pushing on this. It's pushing on what? But through that, it's pushing on what? Through Newton's third law, not through the applied force itself. So what's the only force I can add to the B? FA on B through this surface. You see, that's the trick. An applied force only acts on the object it's physically touching. You cannot put it on the FBD of the other, even if it causes it to move. Nope. You have to transfer it using Newton's third law. So FA on B. Can someone read the question? What's the final part of the question? What is the what? Come on. What's the magnitude of what? Force that. So is it this one or this one? Or either. What's Newton's third law? Both forces of the pair are what? Equal in magnitude, which means technically, if you find this one, or would you be the exact same number? If you're not, that means this world should not exist the way it does. Newton's third law is one of the main reasons you're alive right now and the universe hasn't collapsed, which means this thing has to come out exactly to be equal to this thing. Opposite in direction, sure, but not different in magnitude. Okay, everyone, do I care about any of the horizontal forces? Sorry, vertical forces, my bad. Why do I not care about any of the vertical pairs? Because not a single object is moving what? Down or? Okay. Can someone tell me now how should I analyze this problem? First of all, how many FBDs do I technically have? One or two? Remember, the Newton's third law, you need how many FBDs? One for one object and one for the reacting object. So, can you tell me which object has fewer forces on it? Fewer horizontal forces on it? B. But do I know FA on B? I'm trying to find it. So can I use the FBD for the B block? I don't have enough information, which means I am forced to use the FBD for which block? The A block. All right, let's go to the next slide, everyone. Okay, using, so let's use, go ahead. Let's use FBD of block A. Am I going to use the Y forces or just the X forces? Because the Y's are balanced. They're good. It's the X ones that I'm not so sure about. So let's start. Everyone, F net X equals MA. Okay. Now you're going to have to tell me, what are the forces on the X-axis on the block A? Come on, look at your diagram. Wake up a little bit. Huh. FA app and what? Come on. By the way, is there any way this system could move to the left? Could you ever push on something, on a bunch of things to the right, and suddenly it moves against you? Which means, what's the direction of motion for sure? Great. Go ahead, add it to this diagram. Motion, and pluses here, and minuses here. And now I have my signs. Everyone go ahead, add that motion direction Basically, it applies to both FBDs. So you just need to do it once. All right? So can someone tell me what goes here now in the place of F net X? Come on. You have signs and you have forces. You just need to tell me which one is plus, which one is minus. Ahmed. Yes, everyone? Positive. I'm going to do it in black. Positive F app minus what? Minus F what? Yes, B on A. Equals MA. Okay, can you tell me which of those variables I know? Do I know the applied force? Come on. Do I know the FB on A? No, if I knew it, the question would be done. Do I know the mass? Do I know the acceleration? No, we don't. We don't? No, we don't. You're right. We don't. Okay, that's fine. Yes, go ahead. Okay, everyone. So how many unknowns do I have here? Can you solve a single equation in one and two unknowns? So go ahead, box it. Okay. Now I have to use the FBD of which one? Come on. So now use FBD of block B. So F net X again equals MA. Come on. What is it for block B? Yeah, only one. Only one thing. Well, one horizontal thing. So positive F A on B equals MA. Who remembers grade 10 math solving systems of equations? Come on, people. Who remembers grade 10 math solving systems of equations? No, relax. This needs to sink in. This will make this so easy to do. Do you remember the two techniques you had to learn for solving two like this stuff? For solving something like this? Come on. 3x minus 5y equals 7 and 2x plus 6y equals 13. Who remembers the two techniques you had to learn? Okay. Whoever's gonna give me just one. Hamad, give me just one. What was the first? Say again. Elimination. What was the other method? Substitution. Do you remember when elimination was super freaking powerful? Huh. Elimination was powerful when something very special was witnessed in both equations. I'll give you a hint. It has to do with the word elimination. When you eliminate something, what does that mean? Do you keep it or do you make it go away? Make it go away. Everyone, question. What if this was that? Look. Would you use elimination here or substitution? Why? Who can point to why elimination here is definitely the thing to do? Ayat, why would you definitely use elimination? Because the negative 6y is going to do what to the 6y? Eliminate it. Do we see that here? Come on. Look at the left side of both boxed equations. What eliminates itself? What if someone says, but those are not the same? What do you tell them? They are the same. Do you see what I mean? They look like they're not the same because we use different subscript, but we know through the law they have to be the what? They have to be the same. So what does this mean? Using elimination, everyone, we could do this. I mean, you could write the equations again, but let's keep it simple and let's add the addition line. What happens to these two things? They what? They cancel out. So I'm not going to cancel out like this, but I will tell you they cancel out. So what survives on the left side? Only what? F applied. Go ahead. F applied equals What plus, oh, by the way, are those two m's the same? So please, let's go back and just do a subscript. Here is MA, and here is MB. By the way, are both of them under the same acceleration? What do you think? Everyone, if I put Josh, if I connect Josh, for example, and Josh is touching Ammar's shoulders, and I push on Josh, and I move them as a train, do they move differently or together? A train moves together, right? Which means the whole system moves with a different acceleration or the same acceleration. Which means you don't need to say A and AB or A1 and A2. It's the same A. Do we know the mass of A? Come on. What's the mass of the big block? What's the mass of the big block? Okay, what's the mass of the small one? 5. So this will be 20A plus 5A. What's 20A plus 5A? 20A plus 5A. 25A. All right, we're almost done. What's F applied? 100. 25A. What's your A? 100 divided by 25, which is 4 meters per second squared. That's not the answer to the question. The question did not ask you what's the acceleration of the system. It asked you how much force do they push at each other at the contact surface. How would I find it out? Yes. How many equations can you use? Obviously 2. But come on, which one of them looks easier? Which one has fewer things to play with? This second one. If you're going to use this one, fine. But then that means you're going to have to move this here. You're going to have to move this here. Now, let's use this one. So that implies from here that F A on B or B on A is equal to what? 5 times 4, which is how much? 20. That's Newton's third law. Remember, I will barely give you Newton's third law problems, but this was a good one because that shows you how to split up the FBD and to keep going back and forth. And most likely you're going to use elimination. Why? Because this is what the law says. The two forces have to be the same.